We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are Wicked Inventions. Coming up, audio speakers. What part does a spider play in their manufacturing process? Fibre optic cables. The high-tech science behind transferring data using glass, light and reflections. The trench coat. What has World War I got to do with fashion? We stitch together the history and science behind this iconic piece of menswear. We reveal the surprising science and amazing manufacture behind these wicked inventions. In the 21st century, you'd be forgiven for taking the speakers of your earphones, home cinema system or laptop for granted. They've become ingrained in modern-day living. But just how did that happen, and how do they actually work?
No matter where you are in the world, you've probably come across a speaker in some form at some point in your life. But all speakers work in essentially the same way, in that they convert electronic signals into movement, very, very minute vibrations of a cone, which then create pressure and push out these sound waves, which we can then hear.
This technology is largely the same in any modern speaker.
So whether the sound is coming through earphones that you're listening to on your way to work, or whether the sound is coming through huge speakers that you find at Glastonbury Festival, it's the same concept that's coming into play.
So, how exactly was the speaker we're all so familiar with developed? Long before we had electronic loudspeakers, horns were seen as the solution to amplifying sound for public address and entertainment. Leading inventors of the time, such as Thomas Edison, all turned to the development of horn shapes to produce the best sound possible. However, these horns were very limited to just how much they could amplify noise. As electricity made its mark in the 20th century, this was all about to change.
1921, two gentlemen called Rice and Kellogg, and they actually invented the first speaker as we would know it. They first sold it in 1926 as a radiola, as it was called, and it further developed further into the 20th century.
It's amazing to think that the huge speakers of music festivals utilise the exact same technologies as the tiny earphones we might use every day. But how are these wicked inventions actually made? How are speakers made, and what has a spider got to do with the production process? Let's find out. Beoplay makes quality portable speakers and headphones for modern urban citizens.
So the concept of the Beoplay A9 speaker was sound as a furniture. And we wanted to create a product that addressed the urban consumer's needs for doing a lot of different activities around the living space. Then we wanted to create a product that, as a furniture, could be taken out and fill the purpose of that specific activity exactly where it was needed. So the first thing of the main assembly line is that we rigorously go through all the different components and subcomponents to make sure that they all live up to our standards.
The speaker housing is made from two parts, the front, which is called the baffle, and the back, which is called the cabinet. Both parts are carefully examined for any imperfections or damages before small pieces of foam and rubber gaskets are added, which makes sure that when the speaker is finally sealed, it is airtight. At a specialist mill, fine-grained wood is being made into the speaker's legs using a process called wood turning. This means it's spun quickly whilst irons chisel away, producing an even cut. A two-belt sander is used to ensure a smooth touch. Then the wood is dipped in oils to preserve it. Finally, the letter A, B or C is burnt into the leg to mark the part. In a separate facility, wool is treated and dyed. A special mixture of the different colours are spun onto rolls of wool thread, which are then woven together in a large weave pattern that was specially designed for its acoustic transparency. That is, it lets sound through well. Back in the main factory, the PCBs, or printed circuit boards, are being prepared. These form the electronics that provide the connectivity for Wi-Fi, USB, Bluetooth and more sources. Wires to connect the different boards are also prepared by cutting them to length and bending into shape. Low frequencies need a large cone in order to move lots of air, creating a large sound wave, which we know as the ground shaking feeling created by loud bass. This large cone is called the woofer and is mounted to a bracket to hold it securely in place as it vibrates. More cables to connect the internal electronics are prepared and attached to a large metal plate, which acts as a mounting point for the PCBs. It also doubles as an electrical ground point to avoid any chance of electrocution. The plastic cabinet is then inspected for damage again before being mounted to a trolley called a spider. This carries the speaker throughout the factory, ensuring it doesn't get damaged during the rest of the assembly process. More foam is added for air tightening before the woofer and grounding plate are installed. The next step is to add the electronics to the cabinet. The ASE is the audio streaming engine of the speaker, and it contains the all-important software that tells the different components how to talk and deal with each other. The PCBs, power board and amplifiers from earlier are added too. A special PCB with capacitive sensors which detect objects disrupting their electrical field is then installed around the top edge of the cabinet. This requires high levels of precision, as it is the main control for the speaker. The next station adds the speaker cones and drivers to the cabinet. These are the magnets that moves the speaker cone to create the sound. 2 mid-range drivers and 2 tweeters provide plenty of acoustic power and slot into ports inside the speaker cabinet, along with temperature sensors that monitor heat coming from the drivers. Software within the audio streaming engine monitors these temperatures and will automatically apply countermeasures if they get too high. In a separate facility, an aluminium ring is being manufactured, which separates the speaker cabinet and baffle, providing a precise gap for a cover to be mounted later. This ring is treated by dipping it in different baths of different acids, anodizing the metal, which colours and hardens it. The ring is then fitted over the cabinet and the baffle screwed onto the ring. A small logo plate completes the assembly of the main speaker cabinet. Software containing special code unique to the manufacturer is loaded into the machine using a separate computer.
So the next step is acoustic testing of the product, as we want to make sure that what was theoretically meant as the frequency response of the speaker is actually what has been produced on the assembly line.
A computer uses sensitive microphones to listen to a specially designed sound. This recording is then compared against what the computer knows the speaker should sound like. If the recordings are similar, the speaker passes and it moves on. The fabric cover is placed over the speaker and a final inspection is carried out. The speaker is securely packaged together with its legs, user guide and power cable, ready to be shipped to consumers. The speaker, truly a wicked invention. They seem like unassuming wires, but fibre optics have revolutionised our connectivity. Now, what is the link between our insides and these clever glass fibres? As early as the 1840s, scientists had noted the ability to control light by projecting it through materials like water. It was observed that light would bend in different ways depending on the angle it travelled as it passed from a dense medium to a less dense one, for example, glass to air. Beyond a certain angle, called the critical angle, all the light would reflect back into the glass. This is a phenomenon known as internal reflection. The light which hit the surface beyond this critical angle was effectively trapped and would continue to travel through the glass. In the early 20th century, pioneers of this technique began experimenting with potential applications. The medical profession started to use light directed along glass rods to illuminate body cavities, and others tried to use bundles of glass fibres as a way of transmitting images. Unfortunately, these applications were not very efficient, as light would lose its intensity as it travelled, a principle known as attenuation. In the 1950s, these limitations were overcome.
Abraham Van Heel and Harold Hopkins were the first people who used fibre optics in terms of working out the physics. They understood how it had to work, and Van Heel was the first person that understood that if you took a glass fibre and clad it in something, which is putting something around the outside, that has a different refractive index than the material inside, you get better transmission. A refractive index is what happens when light hits it. If it has a low refractive index, light will bounce one way. If it has a high refractive index, it'll bounce the other way. If you change the refractive index at that area, at the join between the outer and the inner, it means that the light stays more in the tube.
A basic optical fibre consists of a core of a very thin piece of pure glass, such as silicon dioxide, which is thinner than a human hair. This is encased within another glass material known as the cladding. The glass that makes up the cladding has impurities added that gives it a lower refractive index than the core to prevent light from escaping. The construction of the wire is finished off with a protective coating that provides a flexible protection. But how does the light travel round corners?
If you put an outer cladding which has a different type of refractive index, it means that light hits that edge and goes, alright, I'm going to stay inside, and bounces around. And because it's sort of bouncing along the sides of the fibre optics, it can go around a corner because it hits the change in direction, hits the corner, keeps going, and bends around the corner, and to the next corner, to the next, which means you can lay fibre optics and you don't have to worry about them being purely straight.
The first optical fibres were actually used in endoscopes by surgeons for peering into the human body, and it wouldn't be until the 1960s and 70s that engineers started to turn to fibre optics as a way of improving telecommunication networks. With the ability to send signals at approximately 2,000 kilometers per second, it was easy to see why optical fibres would be favoured over metal wires that had been transmitting telephone signals since the 1880s.
It's a big, normal cable that we understand, but it uses light because the fidelity of light is a lot easier to deal with over long distances rather than electrical power, because that involves sending electrons through a system and is much more power hungry. So fibre optics are made cheaper, faster, and more power-efficient electronics to send data across.
Arguably one of the most impressive feats in fibre optic engineering was the installation of the first ocean-spanning optical fibre, the TAT-8 transatlantic cable. Stretching over 3,500 miles from Tuckerton, New Jersey in the US to Weymouth Bay in England and Penmarch in France, it was installed in 1988 at a cost of $335 million. Measuring just over 2 centimeters in diameter and including 6 optical fibers, the TAT-8 cable could handle 40,000 simultaneous phone calls with its light signals traveling up to 40 kilometers at a time before needing to be amplified. An engineering marvel. So, what signal is the beam of light actually sending?
Fibre optics work based on the principle of sending zeros and ones, so on and offs, down a line. In fibre optics, their on and offs are flashes and pulses of light. The faster you can send pulses of light, the faster you can actually send data. So if it's sort of on, off, on, you have your 1, 0, 1, but if you can send it a lot faster, you can send more data and you can achieve higher transmission speeds. So what you have is at one end is you have a light emission system that sends light down it. It gets received at the other end interprets it, understands it, and then importantly relays it. So it takes the signal and amplifies it again if necessary, and sends it down another fibre optic line to the next point, and then to the next point, and to the next point, and at some point that reaches the device it's intended for.
Transmitting high-speed data by bouncing light through glass might seem impressive enough, but scientists and engineers have come up with even cleverer ways of improving fibre optic speeds. To begin with, there are 2 different types of optical fibres: single-mode fibre and multi-mode fibre. At less than a third the width of a human hair, single-mode fibres are incredibly thin and can carry a single signal up to 100 kilometers. Multi-mode fibres don't have the range and are 10 times the thickness of single-mode fibres, but can carry more data by allowing multiple signals to be sent at the same time by light travelling along different paths. And there are other techniques that will keep fueling data transfers ever-increasing speeds.
The best way to deal with fibre optics is lots and lots of thin wires in a very small compact space, and that allows you to send multiple channels of data through one pipe. And then if you can use different frequencies of light, you can imagine that red light is sending one communication channel, blue light is sending another communication channel, and green light is sending another communication channel. You can then send different data streams down the same fibre and then have multiple fibres within the same pipe. You can increase the throughput.
With the current data transfer record of 2 petabytes, now that's 2 million gigabytes, being transmitted in a second over 31 kilometers, it seems data-wise we're going to become even better connected. Can we create a water fibre optic cable? We're going to need a plastic bottle, a laser pen, a drill, and some water. To begin, we create a 5mm hole in the bottle. Keeping a finger over the hole, we fill the bottle with water. We remove our finger from the hole and shine the laser pen directly behind the water, now pouring out of the bottle's side. The water should be pouring out in a curved path. Place your hand through the spout of water well below the hole. You will see that a beam of light is focused on your hand. The light is being guided in the same direction as the water. As we have seen, the light from the pen bounces off the insides of the water spout at a shallow angle, like fibre optic cables. This happens even if the water curves, because the light is continually internally reflected as it travels through the liquid, causing the light to gradually follow the water's path. Can we create a water fibre optic cable? Yes, we can. Wicked challenge smashed. The trench coat dates back as far as the latter stages of the 19th century. But just how did this wartime essential become the iconic fashion piece that it is today? It is hard to forget that the trench coat originates from warfare, but it was the rivalry between two popular outfitters that kick-started this quintessential item of clothing, introducing it into the harsh trench environment, which is where its name was made.
There were two major sort of gentlemen's outfitters who established this sort of outdoor gear, and there was Acoustic and Burberry, and we all know those names today. So Thomas Burberry, who started the fashion brand, he actually established a fabric called gabardine. It was this sort of elusive fabric that was weatherproof but would also breathe. At the same time, they were providing uniforms for the military, and military uniforms were also evolving at this time.
Army officers began to wear the coats as the First World War began, but they were not regulation uniform. It wasn't until halfway through the First World War that this material saw itself on the front line.
The main issue was that in the trenches of the First World War, it was cold, it was snowy, it was wet, it was muddy. The outerwear for officers was these long woolen coats that often were very heavy and very difficult to move in. It was essentially the development of this particular type of outerwear coat that created what we now know as a trench coat.
The development continued, and the designs were adapted to include shoulder straps and D-rings for attaching insignia and accessories. After the war, veterans continued to wear trench coats on their return to civilian life. Their popularity only increased with appearances on film, with many famous cinema characters adopting the trench coat of film noir thrillers. So, how is this iconic item made today? Private White VC is a luxury menswear brand based in Manchester, England.
Private White VC was named after Private Jack White, a World War I military hero. He started his apprenticeship at this very factory and worked his way up from apprentice pattern cutter to factory owner.
They have been making trench coats here for over a century.
The company has been producing outerwear for some of the world's most luxury brands for many, many years. In 2010, when his great-grandson, James Eden, took over the company, there was a case of why are we making these outerwear pieces for other luxury brands when we can make it for ourselves?
Coming up, we'll find out how a fabric can keep water from getting in, while simultaneously letting air out. The production process for making a trench coat starts with pattern making. The pattern cutter makes a template for all of the fabric shapes needed to make the jacket, based on a design provided by the creative director. A sample jacket is then mocked up from the pattern and applied to a fit model.
The fit model will then do all the usual movements, so move the arms, walk in it, sit down, and we'll be able to tweak the pattern then by pinning the jacket in any places that need alteration.
Once altered to the perfect fit that allows freedom of movement, a final card or paper 2D pattern is created, ready to cut the fabric. There are around 700 patterns created in the factory each year. Next, the 2D pattern is digitized into a computer. From here, the pattern is graded, where all of the different sizes are generated, from extra small right through to extra extra large.
At that point, the pattern will then go upstairs to the factory floor, where the cutters will cut the pattern, and they can cut anything from 2 pieces of fabric to 100 pieces of fabric.
On the cutting room floor, layers of Ventile are piled on top of each other. Ventile is a high-performance fabric, which is both weatherproof and breathable. The fabric is constructed from a very fine cotton, woven into a very dense Oxford weave. The cotton fibres expand when they come into contact with water. The combination of fibres, yarns and weave causes expansion in a uniform manner, which closes the gaps and prevents the passage of water through the fabric. The lack of synthetic material in the fabric still allows it to breathe naturally, thereby preventing internal condensation in the clothing. Next, a paper pattern is placed on top of the layers of fabric. Then it's all held in place by table clamps and weights. The pattern pieces are then cut using bandsaws. The collar, hem and sleeve sections are put through a fusing machine. This heats 2 pieces of the fabric to 140 degrees Celsius, which fuses them together to create a level of stiffness to these pieces.
At this stage, they move down the floor onto the factory floor for sewing. On the sewing floor, there will be certain sections of we call them lines, where they will be doing certain sections of the jacket. So you'll have one line will be doing the lining of the jacket, one line will be doing the collar, one line will be doing the sleeves. And at each stage, the jacket is pressed to make sure that when it all comes together, there are no creases or wonky seams.
After this, a waterproof tape is applied to the inside of the jacket's seams to increase water resistance. The final step of the process is finishing and quality control. The jacket is pressed and studded to ensure that there are no creases and that all of the components of the jacket are intact and up to spec.
1 in every 10 jackets will be checked against the spec to make sure that the sizing's correct, that every element of the jacket has been made to the right dimensions, and we allow a 0.5mm discrepancy on any size on any piece of the jacket. If it's out, we take it back upstairs where it will be started again.
From here, the jackets are sent out to stores and wholesalers worldwide.
An SP4 takes around 262 minutes to make, and that will vary from the 40 minutes to cut the fabric to the 15 minutes to do the final QC. We make around 3,000 per year, and they go out to our retail stores and our wholesalers, and we have around 350 pieces per week going through the factory floor.
So, there you have it, the trench coat, keeping people warm and dry since World War I. Very much a wicked invention. So, there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Audio speakers, fibre optic cables, and the trench coat. All wicked inventions.